Hi everyone. So in this video, we're going to do a DC analysis of this common source voltage divider biased amplifier. So this the active device here is an N-channel JFET, and we're going to figure out what the expressions are for VGS. That's the voltage drop across gate and source. ID, the drain current. VDS, the voltage drop between drain and source. And then you have the voltage at VD, VG, and VS, the drain, gate, and source, all with respect to ground. And at Q point. If you remember, Q point means quiescent point, i.e. quiet point, when there are no signals coming in. So first thing we got to do is we need to um, open up all capacitors because we are doing a DC analysis. So frequency of DC is 0 hertz. So the impedance of capacitor is 1 over j omega c. And since omega is 2 pi f and f is 0, so therefore the impedance of capacitors are infinite, 1 over 0, right? So that's the first thing we do. We break these guys apart, remove all signal source, and then we'll use we'll figure out what the current and voltage expressions are around the circuit. All right. Okay. So first thing we do is, of course, open all the capacitors. So what you're left with is this. So you have C1, C2 being open, right, and then the bypass capacitor or shunt capacitor is also will also disappear, meaning leaving just RS over here. All right. So next thing we do is label all the currents that we have around the circuit so that it's easy for us to come up with expressions. So first one I want to put is the current that goes through at the top there, going through R1. All right, so that's okay, so I call it IR1. And then the current going down through R2, that's that current there. All right, and then you have a current going down RD, the resistor at the drain. And then you have the drain current. So that's coming down through there, right? So drain current going into the drain of the FET, JFET. And then you have the source current coming out of the source node. So that's called IS. And then you're going to have the current going through RS. That's that one there. And we're going to have a current that goes into the gate, which will be 0. Okay, so that's going to be 0. So that's over here. So this is a typical characteristics of FET devices. So for whether if it's a MOSFET or JFET, we consider IG to be 0. Okay. Next, let's label all the voltages. So we have VRD, that's the voltage across RD. We have VDS, that's one of the voltage of interest for us in this question. We have a VRS, that's voltage across RS. And the other voltage of interest to us is VGS. Okay, sorry, let me just put this up here. All right. So VGS is this. So that's the gate to source voltage. All right. All right. So remember that we're figuring out all these expressions at the Q point. There are no signals coming in. All right. So let's write out some expressions for the currents, for example. So, well, we know that since there's no IG going in, that means whatever ID that comes into the drain will exit IS, and it will go down through RS. So in fact, all of these currents, IRD, ID, IS, and IRS, are all the same. So that's going to be our first equation. So ID is equal to IS, which is equal to IRD, which is equal to IRS, right? And what is it equal to? Well, it's equal to this expression here. For a JFET, this is the expression for ID. It's IDSS times 1 minus VGS over VP all squared. So IDSS is the saturation drain source current, VP is the pinch off voltage, and VGS is the voltage across gate and source. So sometimes you see it as VGSQ, meaning the value of VGS at the Q point. All right. and also IDQ instead of ID, they might say IDQ for the same reason. All right, so that's our first expression, fairly straightforward. Okay, so let's work out the before I get to IR1. Well, I guess we can look at R1. I mean, let's have a look at IG. When IG is obviously 0, so I'm just going to repeat that here. So IG is equal to 0 amps, right? Now let's have a look at IR1. Well, if IG is equal to 0, IR1 is going to be equal to IR2, right? So whatever current that comes down this branch is also going to go through R2. So we can write IR1 is equal to IR2. Okay? So we got some, so I think that's all the currents. Yeah, I think that's all the currents we have here. All right, so now let's have a look at the expressions for the voltages. All right, so let's start with VRD. Well, VRD is well, should be obvious from Ohm's law. You know, V equals IR, I is IRD times RD, and since IRD is just ID, so that's just ID times RD, right? Okay, so that's VRD. And then you have VRS. Let's have a look at VRS. We'll come back to VDS in a bit. So VRS is just simply equals IRS times RS, right? And since IRS is just ID, so therefore it's just ID times RS. Okay. So let's have a look at the voltages of the terminals of the transistor. So at the drain, gate, and source. So VD, VG, and VS. All right. So let's look at VD first. So what is VD? Well, VD is the voltage drop from the drain terminal all the way to ground. So that's its entire height. Okay. So we could say it is VDS plus VRS. That's one way of doing it. But since we haven't worked out what VDS is, so instead of that, I'm going to use a VDD. Right? It's VDD minus VRD. So this is again KVL. So VDD is from the top all the way to the bottom. If you subtract from VRD, then you will get the rest of the voltage, i.e. VDD. So VD rather, right? So VD is just VDD minus VRD, right? Since we know what VRD is, it's just ID times RD. All right. So that's VD. Okay, let's have a look at VS. Well, VS is just basically, so that's the source voltage with respect to ground, which is equal to VRS. So we have an expression for VRS. So therefore, it's just ID times RS. Okay. So that's our VS. And finally, let's work out what VG is. Well, where is VG? VG is here. Now, VG is a bit different. Since there's no current going into the gate, you can see that the entire left arm of the circuit is actually a potential divider of VDD, right? So VG, that means the voltage here, right, from between gate and ground, is essentially a voltage divider of VDD across R2. All right, so we can write in terms of the potential divider or voltage divider. So VG is equal to VDD times the potential divider part, right? So it's going to be R2 divided by R1 plus R2, right? Okay, so that's our VG. Just put a space there. Okay, so that's our VG. Okay, so now the last part we need to work out are the remaining two. That means VGS and VDS. So let's work out what VGS is first. So VGS, you can write it as VG minus VS. All right, and VG is this term here, right? And then minus VS, and VS is this term here. Okay. So yeah, we can't simplify this anymore. So that's the expression for VGS. And finally, for VDS, it's just simply VD minus VS. VD is this expression here. Minus VS. VS is this expression here. Okay. So we can factor IDs together. So that's VDD minus IDRD minus IDRS. So we can write as VDD, okay, minus ID, and then in brackets RD plus RS. Yeah. All right. So that's the expression for VDS. Okay. So now I'm going to bring in how these two equations relates to our load line on a typical input and output characteristic curves of a JFET device. All right. So first of all, you convert it into y equals mx plus c form. Okay. So I have this one for the input characteristic curve, because the input characteristic curve, I'll bring it up in a bit, is a graph where the vertical axis is ID and the horizontal axis is VGS. All right. And for the output characteristic curve, the vertical axis is ID and the horizontal axis is VDS. All right. Okay. So once we have them in this form, we can then have a look at it in terms of how it looks like on the actual curve. All right. So if you look at this is the input characteristics. That's the device equation, a device curve, quadratic curve from this quadratic equation. And you have this load line that comes from here. Yeah, ID equals to all of this. Yeah, that's the equation of that load line. So at VGS equals 0, at VGS equals 0, that means this term becomes 0, right? So then ID is simply equals to all of this. So that's what that is. So that's the value of ID when VGS equals 0. And then down here, when ID equals 0, well, when ID equals 0, that means, the denominator is the same. So that means VGS has to be equal to this. Yeah, VGS would have to be equal to this value. Then you get an ID of 0. So that's what you get here, right? So that's the value at the x-axis intercept, if you like, the value of VGS. Okay. And then on the output characteristic side, okay, so this is the output characteristics, typical output characteristics. You have the load line of this line here. So you have that straight line, a load line equation that we saw earlier. And at VDS equals 0, well, when VDS equals 0, then ID simply equals to this term, which is what that is. And then at ID equals 0, that means when ID equals 0, the only way you can get 0 is if VDS is equal to VDD, right? So that's why you got VDS equals to VDD at that point, all right? All right, so I hope that helps in understanding how the equation relates to the behavior of the circuit and what kind of biasing we need in order to get the kind of signals that we want when we do our AC analysis, all right? Thanks for watching. See you next time. Bye-bye.